So if we want to figure out where the function is increasing or decreasing without relying on a graphing calculator, we can take a derivative, because the derivative tells us values where it's increasing. That would be positive for the derivative, and where it's negative. So that'd be where, if the derivative is negative, it's decreasing. So let's do quotient rule. It's our top function, this is our bottom function. So it's a derivative of the top function. So the 2/3 comes down, then we reduce this by 1. So 2/3 minus 1 makes negative 1/3. Then we multiply that times the bottom function kept the same. Then subtract that by the top function kept the same, times the derivative of the bottom function. Then it's all over the bottom function squared. Okay, so pretty ugly, but that's the derivative. I don't see a lot of ways we could clean up, make it a lot nicer here in the top. I think this term is as quote unquote nice as it can be over here. You can make that be here. If it's x to the negative 1/3, we can make that look a little nicer. That's x to the 1/3 in the denominator, right? So it's the same thing as a cubed root. So I made this positive by putting it downstairs in the denominator here. And over here, we got x to the 2/3 times 2x, so the power of 1 and the power of 2/3 adds to make x to the 5/3. Oh, I forgot to square this. It's not going to matter, but okay, so that's the derivative. So if we want to figure out where it switches from increasing to decreasing, we want to know critical points. Because the critical points aren't necessarily maxes or mins, but they're at least all the different places where you could reach the maxes or mins. They're all the places where we could switch from increasing to decreasing, or vice versa. So we set the derivative equal to 0, multiply both sides by 5 plus x squared, and that gets rid of it because times 0 over here. We really just want to figure out what would it take to make this be 0. The other thing you want to check with critical points is where would the derivative fail to exist. But 5 plus x squared is never going to be 0. Okay. So we're all set there. Okay, so solving this part, it's not very pretty, is it? So let's try distributing. 10 over 3 cubed root of x. And then this is x to the negative 1/3, right? So if we multiply that to 2, then you got 6 over 3 minus 1 over 3. That makes x to the 5/3. So we've got 2/3 x to the 5/3 here. In other words, what I did was get x squared divided by x to the 1/3 power. So the power subtract 2 minus 1/3 makes 5/3. And I did that because I saw that we're going to have like terms, I should say. But before we even resolve those like terms, yeah, I mean, you could combine those. But look, you got a cube root of x in the denominator. That's going to be hard to solve if it's in the denominator. Oh, actually, so here, this is our derivative. The derivative would fail to exist if x equals 0, right? So that's one place we got to keep in mind. Sorry, I missed that one. There was no divide by 0 problem here, but there's a divide by 0 problem here. So that's one of our critical points. Okay, so trying to solve, if I'm trying to get x by itself, I'll never get it by itself if it's in the denominator. So let's multiply everything to the 1/3 power, because that will keep it balanced. Cancel out the 1/3 down here. And that makes 2/3 x squared. And that's going to make minus 2x squared here. So this is 6 over 3. So 2/3 minus 6/3 makes negative 4/3. So this is 0 equals 10. So it's a much easier equation finally. So I can add that 4/3 to both sides. Multiply both sides by 3/4. And use the square root of both sides. So x would be positive or negative square root of 5 halves. Okay, so those are the critical points, and what you want to do is test numbers to the left and to the right using the derivative to see whether you switch from increasing to decreasing. So if this is the derivative on a number line, I'm too tired to even think about what square root of 5 halves would be. Square root of 5 halves and negative square root of 5 halves. Oops, square root of the whole thing. So this would be negative 2, that's something to the left. Here's 0. Here's square root of 5 halves, and then 2 would be something to the right. So these are derivative values. If I plug in 0 into, oh, I get undefined, that's right. So I'm not going to be able to plug in 0 into the derivative. I can plug in 0 into the original function though. So let's use the original function. We can still get the same results. We just need to know the y values to find out whether we went up or went down. So if I plug in 0, I've got 0 divided by 5, so that makes a y value of 0. And if I plug in something to the left of this critical point, I get negative. So negative 2. I don't really want to do that though. It just takes a long time. Man. The original function. Okay, so here, if I plug in negative 2 in here, I'll help you do this without a calculator in just a bit. But if you're doing this and you just want to get your homework correct, you could pull out a calculator, right? What am I doing? I'm plugging in negative 2. Okay, so that's negative 2 squared makes 4. So we got 9. And then up here, negative 2 to the 2/3, that's the same thing as negative 2 over the cubed root of negative 2. Oh, I guess we can't anyway. Still gonna be, we still need a calculator no matter what. But look, these are the same. Negative 2, that's negative 2 to the first power. This is negative 2 to the 1/3 power. The powers that subtract when you divide. 1 minus 1/3 makes 2/3. Doesn't really help us. Let's see, if I actually go over to the number line, if I plug in negative 8, then that would turn out to be something nice. That'd be negative 8 over the denominator would be cubed root of negative 8 still, and that'd be 8 squared is 64 plus 5, that's 69. Oh, just use a calculator. These numbers are way too low. Okay, I plugged each of those into the calculator. And I got y values of 0.176 for a number slightly to the left of our critical point. And then a number to the right of our critical point, we got 0, so that this would be a max. That means we were increasing to the left of here, and then we went back down to 0, so we were decreasing this way. And then once we got to our next critical point, then we started increasing up to 0.181, and then we went back down. So it's decreasing from negative infinity, decreasing from negative infinity to our first critical point. It's all inside the square root. Oh wait, sorry, that's increasing. It's increasing because it's going up, right? It went up from 0.176 to 0.181 once we hit our critical point. And then that's increasing, and then it's decreasing from that critical point, negative square root of 5 over 2 to 0. And then it starts increasing again from 0 to square root of 5 over 2. And then it starts going back down. So it's decreasing from that critical point to infinity.